Welcome to day 3 of sequences, and today we are going to focus on the geometric sequence and just the explicit formula. So remember a few days ago when we started talking about geometric sequences, we talked about how a geometric sequence has something called a common ratio. And that common ratio, we use the letter R to represent that ratio that multiplies each term to get to the next. And it can be a whole number, it can be a fraction, it can be a decimal, it can actually also be positive or negative. And geometric sequences represent exponential functions. Okay, exponential functions, it could be growth or decay. If our common ratio is negative, it's actually something called an alternating sequence, and that wouldn't be growth or decay, but typically it's either growth or decay. And therefore, the common ratio can be compared to the growth or decay factor. So let's take a look at two examples here, just to refresh our memory. So to get from 4 to 20 and then 20 to 100, it's clearly growing at a very fast rate. It is not adding by the same amount every single time. Let's figure out what it's multiplying by, and hopefully you agree that it's multiplying by 5 each step of the way. The value of the first term is 4. So if this is the first term, 20 is the second term, 100 is the third term. So if I wanted the fifth term, I would have to extend this out, get 500, and extend it out one more time, and I would get 2,500. And if you can hear the lawnmower next door, I apologize. Number 2, it starts at 810, but then clearly it's decreasing, and not by subtraction, by multiplying by something. And if you can almost ignore these zeros that are at the end, if you went from 81 to 27, 27 to 9, it might be a little bit more obvious that we are multiplying by a third. All right, so if 810 is the first term, 270 is the second term, 90 is the third term, and I want to make my way all the way out to the fifth term. Well, 90 times a third would be 30, and 90 times a third would be 10, so that must mean the 10th term, or the fifth term is 10. So extending a pattern is useful if you only have to go out a few terms, just like yesterday. But what if I wanted you to go out to the 50th term? Are you going to sit there and do multiply by a third, multiply by a third, multiply by a third every single time you wanted to get out to the 50th term? Hopefully you say no. So we came up with also an explicit formula, but for geometric sequences. Now this also would be given to you on your reference sheet, and it will be given to you on your reference sheet in 2 years when you make your way to Algebra 2. But for now, let's take a look at it. You need the following things to be able to write the equation of an explicit geometric sequence. You also need the first term. Just like yesterday, you need to know A1. And just like yesterday, when you needed to know the common difference, today we need to know the common ratio. Now, we just finished a unit on exponentials, and we kept saying that our equations looked like this. And they still do. Remember, this front number was our y-intercept, or what we considered our initial amount. That's the exact same spot that A1 is in that represents the first term. And didn't we say when we had our exponential that this was either our growth or decay factor? That's exactly what the R is in an exponential. The only change that is happening is that the exponent is an n minus 1, just like the formula for arithmetic sequences. So this formula is what we're going to be using on the next corresponding examples. Here are the first 4 terms of a geometric sequence. So obviously if the sequence starts with a 2, that's the value of the first term, second term, third term, fourth term, and so on. To get from 2 to 8 and then 8 to 32, I hope you agree that it's multiplying by 4. Once you know those two things, to write an explicit formula for the sequence, you start with an is equal to your initial amount, your value of your first term, parentheses, common ratio to the n minus 1, and you're done. That's it. That's your answer. And then if I want the 6th term, I plug in a 6. That's an A, not a 9. A sub 6, 2, 4, 6 minus 1. So if I want to find the value of the 6th term, I just type into my calculator that. So let me bring up my calculator here. Gotta turn it on. Clear? 2 parentheses 4 raised to the 5th power, 2048. Now you can confirm this the same way we did before, because we only are going out to the 6th term right now. If I did 128 times 4, that's 512. And if I did times 4 again, that's 2048. So it checks out. All right, let's try a few on the next page. Now, I'm not going to do every single one. I'm going to select the ones that are the more difficult examples than the easier ones. So feel free to try A and B on your own. It says write the explicit formula and then use it to find the 7th term. So remember, our formula looks like this. So let's take a look at letter C. -3 is the value of the first term. And how do I get from -3 to a +9, a +9 to a -27, a -27 to a +81? So clearly the signs are alternating. 3, 9, 27, and 81 it should be a familiar sequence to you guys. It is multiplying by a -3 as well. So my formula would say an is equal to -3 parentheses -3 to the n minus 1. And then if I want to use that to find the 7th term, I just have to plug in a 7. I can type that in my calculator exactly as I see it. So if I bring up my calculator, -3 parentheses -3, close it, raise it, 7 minus 1, enter, and there you have it. That would be the 7th term of the sequence. All right, let's take a look at letter D. Now this clearly is a sequence that is going down. So A1 is 200, but we need to figure out the common ratio. So what am I multiplying by to get from 200 to a 50, and then 50 to a 12.5. And sometimes the easiest way to figure out that difference is actually to take the 2nd term, divide it by the 1st term, and that will help you find your common ratio. So once you figure out your common ratio, you can always check it, okay? Just because you got a number doesn't mean it has to be true. So let's check it. 200 times 0.25, that equals 50, times 0.25, that equals 12.5. So it checks out for the first 3 terms, so we're good. All right, let's write our equation. So A sub n is equal to 200 common ratio to the n minus 1. And then if I want the 7th term, I just have to plug in a 7 where n is. Type it in my calculator. So 200 parentheses 0.25, close it, caret to the 7 minus 1, enter. And that's a long decimal. Do not round it. Actually, what I would prefer you to do is hit math frac, and that will give it to you. That will give you your answer in the simplest fractional form. All right, I actually think number 5 is too easy for us to take our time to work on now, but feel free to do that on your own. Take a look at number 6, though. This is asking us to find the 8th term when the first term is 1 and the 3rd term is 81. So sometimes I like to do this little skipping method. The first term, the 2nd term, the 3rd term. The first term is 1 and the 3rd term is 81, and they're telling me it's geometric. So I need to figure out 1 times something times that same something gets me to an 81. So 1 times what times that what again would get me to an 81. And I hope 1 times 9 is 9, and 9 times 9 is 81. So now we can figure out that our common ratio is 9. Our value of our first term is 1. So our formula would be 1 parentheses 9 raised to the n minus 1. And if I want to find the 8th term, I just plug in an 8. Now this number does get very large. We learned that in our exponentials unit. Exponentials grow or decay very quickly. Oops. So expect to get some monstrous numbers in your notes and on your homework. So there it is, 4,782,969 would be only the 8th term in the sequence, which is kind of crazy. All right, let's do number 7. In a physics experiment, Dan drops the ball from a height of 16 feet. So if he drops the ball from a height of 16 feet, that sounds like an initial height. Each bounce is 70% of the previous bounce. And that should make sense because if you're dropping something off from a height of 16 feet, each bounce after that is just going to get smaller and smaller and smaller. So it should make sense that it's only going up to 70% of the original height. Okay, I'm going to erase that little drawing there. All right, so, but if it's bouncing up to 70% of its original height, then that actually is our common ratio. So our common ratio is 70%. Write an equation to determine the height of the ball after n bounces. So if I am multiplying by 0.7, that is a geometric sequence with an initial value of 16, a common ratio of 0.7, and raised to the n minus 1. And after how many bounces will it be less than 2 feet in the air? So what I suggest is to type this in your y equals screen. You won't learn how to do this algebraically until you get to Algebra 2. But essentially what we are trying to find is what n is, okay, what is n when the equation equals 2? So if I can type this in my y equals screen, let me go to my calculator, bring that up, go to your y equals screen, and type in 16 parentheses 0.70, close it, caret to the x minus 1. Go to your table, so second graph, and what I would like you to do is, there it is, the value of the first term is 16, that's just like we said. That means after one bounce, it's at 11.2. After 2 bounces, it's at 7.84. After 3 bounces, the ball will be 5.4 whatever feet off the air or whatever. So it wants to know after how many bounces it will be 2 feet off the air. So I'm going to transfer this over because I know the minute I touch my page, it's going to go away. So n and a sub n. The first initial drop was 16. This was 11.2. I'm just getting these numbers from my calculator. I just had it on the screen. Okay, so I'm just copying this over from there because I can't write on it and have the calculator up at the same time. So just trying to jot these down real quick. Okay, so let's think about it. 16 was its initial height. So that means this is the height of the first bounce. Okay? This would be the second, third, fourth bounce, fifth bounce. So I would say after the 6th bounce is when the ball will start being less than 2 feet off the ground. All right, just a few more. So number 8, it says Danielle's parents have offered her 2 different options to earn her allowance over a 10-week period over the summer. So option 1, she can get paid $10 additional each week. Or option 2, she will get $1 for the first week, $2 for the second week, $4 for the third week, and so on. Does the second option sound like a geometric sequence? And I hope you would agree that it would, because the sequence was $1, $2, $4, and so on. So her allowance is doubling which means every week. So that means her common ratio is 2. So it is multiplying by 2. So yes. Part B says, consider the 8th week of summer. How much will she make in option 1 versus option 2? So let's think about option 1 for a second. Option 1 says she will get paid $10 additional each week. So in my head, that means for option 1, her initial salary is $10 a week, and then she's getting paid an additional $10 each week after that. So her common difference is 10. So that sounds like an arithmetic sequence. So our formula for that, remember, is AN, the initial amount, plus n minus 1 times the common difference. And it wants to know after the 8th week. So let's plug in an 8. So if she goes with that method, she will be making $80 that week in the 8th week. So now let's go with option B. Well, not really option B, the second option, which I'll call the geometric option. So option 2. Option 2, she's starting with $1, and her common ratio is 2. It's doubling. So AN is equal to her initial amount, common ratio to the n minus 1, and again, we want the 8th week of summer. And if I plug that in my calculator on the 8th week, she's actually going to be making $128. And remember, that's only the 8th week. This is over a 10-week period. So, if you had to choose, though you might not get a lot of money up front, you're going to get a lot more money once you get to the 10th week if you go with the geometric option, because it's growing exponentially. All right, 2 more examples, number 9 and number 10. So number 9, use the explicit formula to determine the value of the first term if the 7th term is 1024 and a common ratio of -2. Okay, so this is interesting. If they are giving me A7 is equal to 1024, 7 is our n value, and 1024 is AN. They also give us the common ratio is -2. So here's our formula, remember. So we are given AN right here. We are given N, which is right here, and we're given R, which is right here. And what we're trying to find is the first term, and that's exactly what they're asking us to find, and that's exactly what we don't know. So let's plug in and solve for it. So if AN is 1024, I don't know A1, common ratio is -2, and N is 7. Let's clean this up a little bit. All right, so -2 come on, okay. Parentheses, -2, close it, caret, 7 minus 1, enter. It's just 64. Oh, that's not bad. There you go, divide it to the other side. And the value of the first term, divide it in your calculator, is just 16. Not bad at all. All right, last example, and it's actually a pretty quick one. It says Kara exercised 2 minutes a day in the first week. So that sounds like her initial amount, or her A1. All right, so 2 minutes a day for the first week, 6 minutes a day for the second week, 18 minutes a day for the third week, 54 minutes a day for the fourth week, and so on. Describe the sequence. So the fact that this sequence seems to be multiplying by 3, I would say something like this is a geometric sequence, because the minutes increase by a common ratio of 3. All right, describe the sequence I did, and then predict whether she will be able to continue this pattern as she increases her exercise time. So this actually is not going to have us compute anything, it's more of a conversation. Will she be able to forever and ever and ever continue to increase the amount of workout time by multiplying it by 3? And pretty much it's a no. She will not be able to continue this pattern forever. I mean, even if I just grab my calculator real quick here, if I do 54 times 3, she's working out 162 minutes in a day. I mean, that's almost 3 hours of working out. So if she even went one more time, oh my gosh, she's working out for like 8 hours a day. That's just not possible. So predict whether she will be able to continue this pattern. The answer would be no. And then you would just explain why it's just theoretically impossible. All right, that is the end of sequences for us. So until next time.